And our next speaker is Lukas Hirsch, and the title of the presentation is Leveraging Multiple Priors for Brain Segmentation.
We see anything here? Okay, so hi. I'm Lukas Hirsch. I'm a graduate student from the Neural Engineering Lab from the Lucas Para in City College, New York. So I'm going to talk about brain segmentation. So there are a lot of tools already available for doing automatic segmentation of images. But we have the experience that in clinical context with biomedical images, segmentation is still a bit of a problem, and we have some difficulties with it. Especially, so current state-of-art segmentation tools work with atlases that are made from healthy subjects, and they are used to assign prior probabilities on tissue location and aspect. But then working in clinical context, we often have abnormalities which are derived from lesions or tumors, and these models are often not flexible enough to account for that. And for example, here we have in the middle a T1 weighted MRI. I don't know what the label went off. And in the middle, this we have a lesion from a stroke. So there was necrosis here in the middle, and the tissue was filled with cerebrospinal fluid. On the left, we have a ground truth segmentation, which we label as the truth. And this was manually segmented, which is a very hard-working task. And on the right, we have the segmentation made from SPM, which is a tool from MATLAB, which is very widely used in our lab. And we see that it fails to recognize this lesion, that it's not expected to be here. And from here, it propagates errors, failing to recognize the rest of white matter and gray matter, making a lot of mistakes here on the cortex. It's another example also. We have a very abnormally enlarged ventricle here in the middle. And SPM expects a small or normal sized ventricle in the middle and makes some mistakes. It labels the surrounding as gray matter, and that error propagates, and it has a weird assumption how gray matter and white matter is distributed in the image. So in natural image processing, as we saw before, deep learning methods have taken over as most successful tools for image recognition and segmentation. Now in biomedical images, so using these atlases or priors hasn't been picked up by the machine learning community so much, because there's this trend of trying to avoid feature engineering process and avoid placing priors to make multi-purpose models that have the least amount of information primarily. Now, we're not so interested in developing artificial intelligence, and we want to try to solve this problem. So our approach is trying to combine the two approaches, which is using priors with a convolutional neural network. As Michael Rosen showed before, these are tools for image recognition. These are deep learning models. So this is the backbone of the model that we're using. This is a 3D convolutional network. So it is trained on recognizing 3D images and segmenting them, which is assigning one label to each pixel in the image. So this model, which we call the vanilla model, because first it doesn't have any awareness of space, location, or morphology. This is just a neural network that is trained on recognizing or taking small volumetric patches from a 3D MRI and predicting the label of the center voxel. So this is all working on volumetric features. So to this vanilla network, we add 3 models that include information specific for this task. First, we add a context pathway. This is a parallel feature learning pathway that just takes a wider field of view from the input image. So that is, it's a similar as a vanilla network, just takes a larger input patch at lower resolution to be aware of context. The second one, we're introducing a tissue probability map as an extra input channel to the network. So this tissue probability map contains values for each voxel in the image and assigns the probability of that voxel belonging to each of the classes that we're trying to label. Now, adding the TPM, the tissue probability map, makes this network no longer shift invariant, because now we're introducing information on absolute location for each voxel or pixel in the image. And third, also widely used with these models, is adding a post-processing model, in this case a conditional random field. This is a structured probability model. So this is a model that assigns probability to different structures. And in this case, the structures is the configuration of our labeled segmentation. And here we're introducing prior information on what we know about brain morphology. So in this case, we're penalizing neighboring labels for classes that we know should not belong together, like voxels that label skin and cerebrospinal fluid, for example. So these are three models that are independent from the central model, and in the following slides, I'm going to show how adding each one of these context models aids on the performance of the network. So first, this is a baseline performance. On the top, we see just a T1 MRI of a subject with an abnormal anatomy, also a lesion here. On the left, we have the result of SPM. On the right, we have the result of just a vanilla convolutional neural network. Now, this convolutional neural network, we trained it end-to-end on a set of 42 heads. 37 from them were from stroke patients that had lesions. And we see that first, this vanilla model makes different types of errors than SPM, but they both do not perform very well. So SPM is not very flexible and cannot adapt to non-standard positions of the head in the MRI, whereas the vanilla network does not care about that, but it's making a lot of morphological errors here, placing skin tissues within the brain and placing brain tissues outside the brain. So we can start adding the different, So to summarize how well one segmentation performs, we use the dice score, which is just assigning a number on how well the segmentation output matches the ground truth segmentation that were manually segmented. So watching the distribution of dice scores, comparing SPM to this first vanilla network, we see the performance is pretty similar, if not a bit worse. There's not much gain to it. But this model is very flexible, so we can start adding the next models. First, for post-processing the segmentations, adding the conditional random fields, this refines the segmentations, accounts for continuity in the image, and already shows a significant increase in the quality of all the segmentations. Then the next thing, adding just the context pathway to the vanilla network, also improves significantly on the performance on all the segmentations. And finally, adding the third model, which is adding tissue probability values for each voxel, also significantly improves the quality of all the segmentations. Now, these three models are independent of each other, and we can put them all into one model, which we call the multipliers. And then we see these accounts for all the problems that we were trying to solve before, and the output segmentation looks pretty nice, and it's solving a lot of the anatomical errors that the other models were doing. This model here is also a curve showing the dice scores on all the different models that we were trying, including state-of-art SPM. We see it's the current outperforming model. Now, this is just a summary of how well the segmentations were matching the ground truths. On the right, we see a confusion matrix to get to be aware of which kind of errors is actually this model correcting. And it's mostly a lot of morphological errors, where the vanilla neural network was placing labels for skin in voxels that were actually supposed to be brain voxels. All the red values means places where the multipliers were correcting these errors. So we're happy with this model, but we want to see how well this performs on different data sets, so with different MRIs that were not trained upon and coming from different scans. So this is a data set containing 52 MRIs from subjects with cognitive disorders. These were all subjects in coma. And they all have very abnormal anatomies, a lot of enlarged ventricles or stroke lesions, or just a lot of issues in anatomy. And these two, they were partitioned into two groups. There were patients who were in so-called in vegetative state and patients in minimally conscious state. I'm sorry, everything got shift here. So vegetative state and minimally conscious states are two different clinically relevant states because the prognosis for each of them is different. Whereas vegetative states have a much more pessimistic prognosis, and it's less likely for them to wake up from a coma. Minimally conscious patients usually have a more optimistic prognosis. There's interest in trying to differentiate one from another. And this is still subject of research, and it's not very clear how to distinguish these two just from imaging. But we know there are two known volumetric markers, which is the amount of volume of gray matter and the volume of cerebrospinal fluid, which has been shown that vegetative state patients have, in general, less gray matter and more cerebrospinal fluid in their brains. So we segmented all these 52 MRIs using SPM and also with our model, the multipriors. And SPM, as again shown before, showed to have unreliable results on the segmentation. We quantified the tissue volumes from the segmentations made for the multipriors and confirmed what was expected, which is comparing the amount of volume in the skull cavity. For vegetative state patients, we see a lower, significantly lower distribution than patients that were minimally conscious. And conversely, the same for the amount of CSF that was in the brain, which was significantly higher in vegetative state. And also quantifying the volume of white matter, we confirmed which was not expected, that white matter does not serve as a marker, which is also known. So it was just a validation out of sample data set. So here I hope that I showed that not only spatial context helped, but absolute location and prior information can be leveraged into these models. And also that although we were using a modest number of heads, because we're training actually on millions of labels from millions of available voxels in the image, we could train a deep convolutional neural network from scratch that generalizes well out of data sets. And thank you very much.
That was great. Do you have time for any questions? Sorry. No questions?
Okay.
Okay. Thank you.